All right, so the final lesson for this module, lesson number 4, we're going to dive into implementing RIP next generation. Not that RIP is an important routing protocol. Fundamentally it's a flawed protocol in many, many different aspects. Even though RIP next generation is classless because it is IPv6, it still has a lot of limitations. It does periodic updates instead of incremental updates. It can only go a maximum distance of 15 hops. But the worst thing about RIP primarily is its metric, right? It chooses its path. Its path selection process is based on hop count. The metric is hop count. And it doesn't take into account at all bandwidth. And you can't change that behavior. So that alone really kind of makes RIP not necessarily the protocol of choice. Back in the day, that would have been okay because we didn't have 1 gig, 10 gig, terabit connections. We had fast Ethernet or Ethernet. In fact, we probably didn't even have fast Ethernet. We just simply had Ethernet connections and not Ethernet connections. So everything kind of looked the same. So hop count worked out very well in that case. So what we're going to do in this chapter, it's a relatively short chapter, but our focus in this lesson is basically going to be on, what are the characteristics of RIP? We'll talk about that very quickly. How do we configure and verify RIP next generation? Then we'll talk about how to share default routes in RIP. And then last, we will wrap up by taking a look at the database. But I'm going to add to this discussion because I think it's important in a sense that a lot of the concepts that we're going to talk about in RIP carry over to some of the other protocols that we're going to be talking about a little bit later on. All right. Now, RIP fundamentally is a distance vector routing protocol. And it's not even necessarily a hybrid. It's purely distance vector. It does periodic updates. In the case of RIP, it sends out updates every 30 seconds. So it doesn't matter if there's a change in the topology or not. I'm going to tell you about the information that I know. Not only am I going to tell you about the information I know, I'm going to tell you about everything I know, as opposed to maybe potentially what might have changed over time. All right. Also, RIP does not scale well. It only goes up to 15 hops. 16 hops becomes unreachable. So from a scalability standpoint, RIP is somewhat of a limited routing protocol as well. In addition, RIP uses hop count as a metric. So in this particular case, because we only have 2 hops to get from PC1 to PC2, as opposed to 1, 2, 3, 4 hops, if we go the fast way, RIP is going to choose to use the top path as opposed to the bottom path because it simply doesn't understand bandwidth as the concept of part of the metric. All right. So it's kind of interesting. It's like, why does this protocol still exist if it has all of these deficiencies? And I'm not sure why. Maybe it's for nostalgic reasons. I don't know. But Cisco still has RIP as part of their operating system. And I have heard from time to time people running RIP. It is a relatively simple protocol. Remember those 3 things that we talked about previously with regard to the 3 major components of a routing protocol, right? The routing protocol messages, the algorithm, and the data structures. Sorry, I lost my train of thought there. The data structures, the routing protocol algorithm, and the messages. So in the case of RIP, it isn't quite the same as like an OSPF or EIGRP. We don't form neighbor adjacencies, for example. There's no formal adjacency process in RIP. We can define neighbors statically, but that's for the purpose of circumventing the use of multicast and simply using unicast to send messages back and forth. But we don't necessarily form full adjacencies. There's no neighbor table that we can look at. There is a topology database and there is a routing table, but that's pretty much it. So we're going to take a look at this from the perspective of this protocol. Before we get into that, let's take a look at one more thing. RIP Version 2 is what we see for IPv4. It rides on top of UDP port 520, uses multicast address 224.0.0.9, supports subnetting, so it's a classless routing protocol, has a metric of 15, uses a metric of hop count, has a maximum metric of 15 hops, and has an administrative distance of 120. Can somebody please describe to me what administrative distance represents? Anybody?
Cost?
Cost in what sense? Are we talking about a metric? What are we talking about? Any ideas?
Yeah, I think it's a metric.
Okay. Let me tell you what it is. All right. First of all, administrative distance is a static value that is assigned by Cisco. Actually, any vendor can decide what AD value they want to assign to a routing information source. But in the case of RIP, Cisco has assigned an administrative distance value of 120. All right. And if I go out to Google, for example, and I search for Cisco administrative distance values, you'll see the entire table. All right. And here is the entire table. All right. So if you look at this, it says here, and that's not a very good image of that. Let's try this one here. All right. You'll see here it says a connected interface has an administrative distance of 0, static routes 1, EIGRP summary 5, eBGP, external BGP 20, internal EIGRP 90, IGRP 100, OSPF 110, ISIS 115, etc., etc., etc. Okay? Now what this value is used for is it's used to define the trustworthiness of the source of information. Meaning that if I learn about the 10.10.10.0/24 network from OSPF, and I learn about the 10.10.10.0/24 network from RIP, because the metrics for OSPF and RIP are completely different and unique, I can't really choose whether I'm going to use the OSPF route or the RIP route based on metric. The tiebreaker is administrative distance, and the lowest value always wins. All right? So it is a metric in a sense, in that it is a metric that defines the trustworthiness of a routing information source. However, it only comes into play if you're learning about the exact same route from two different sources. So if I'm learning about the 10.10.10.0, let me change that, 10.10.0.0/16 subnet from RIP, and I'm learning about the 10.10.0.0/24 network from OSPF, both of those routes go in the routing table because they're different prefixes. One is a /16, one is a /24. They might both represent essentially the same destination, but because they're not the exact same route, administrative distance doesn't come into play in that particular case. Does that make sense? So administrative distance is probably not something you're going to see too often, because you would literally have to be running multiple routing information sources. All right. Like RIP, like OSPF, like EIGRP at the same time. You would have to be learning about the exact same routes through those processes, and then the router would have to make a decision on what routing source to use. All right. So by definition, the official definition of administrative distance is it is a numerical value that defines the trustworthiness of a routing information source. Okay. And clearly, RIP is kind of high on the list, right? EGP, remember EGP was the very first routing protocol? classful exterior routing protocol 140, on-demand routing, external EIGRP, internal BGP. You should never route with BGP. BGP is very slow, it's very inefficient. It's used to route between autonomous systems, not inside of an autonomous system. That's why internal BGP has such a high number. But you know, EIGRP, yeah, I guess that could be more trusted than IGRP. IGRP was classful, whereas EIGRP is classless. But Cisco decided that they're going to rank IGRP on top of OSPF for some reason. I guess it is their protocol. They get the choice to do that. But certainly OSPF is a much better protocol than IGRP. All right. Other vendors, they're going to have a different scale. They're going to have a different way of identifying the trustworthiness of a routing information source. Of course, the most trusted is your connected routes. Makes sense. They're connected to the router directly, so they would obviously be the most trusted routes. Okay? So in this case, administrative distance is 120. Routing updates are sent out every 30 seconds periodically, which is ridiculous because I should only send out routing updates when something changes. So routing updates are sent out periodically or whenever there is a topology change. That's called a triggered update. Otherwise, I'd have to wait X amount of seconds for the update to propagate. Both of these protocols support authentication. So the only difference between RIP Next Generation and RIP version 2 is it runs on UDP port 521, and that's it. It's just as bad as RIP version 2. It's not quite the same. You know, Star Trek The Next Generation was significantly better than the original version of Star Trek, but I digress. RIP Next Generation, just as crappy as RIP version 2. Nonetheless, it's still something that we talk about because they're, number one, it's IPv6, which I think is a good thing to discuss. All right. So in this discovery number one, and like I said, we have almost over 20 discoveries in this course. Throughout this discovery, we're going to basically learn how to configure RIP Next Generation. We're going to configure basic RIPng on router 2. It's already configured on router 1. And then we also have a static default route that points over to the internet. We'll take a look at R1's configuration before we get into doing R2's configuration. So there's two tasks that we want to accomplish in this particular exercise. I want to be able to configure RIP to work between these routers. Then I want to make R1 share its default route through the RIP process to router number 2. I don't want to do a static route. All right. And then we have some route on the internet that we're using to simulate the topology. Okay, or to simulate the environment. So this is our visual objective. We're going to share the default route on router 1 over to router 2. Let's take a look at that default route on router 1. Here's our topology. Let me go into the console real quick. All right, and I'm just going to do a quick show run section RIP, and you can see the RIP configuration. No network statements. You guys are going to see this when we implement EIGRP and OSPF for IPv6. We don't use network statements anymore. In fact, we enable RIP globally by starting a RIP process. In this case, it's called CCNP_RIP, case-sensitive name. And we simply enable RIP on the interfaces that we want to run. So if I do a show IP route connected, you can see here, that's weird. Oh, I'll bet you my interfaces are shut down. Don't have my config here. Hold on one second. Sorry about that. I had to paste in the configurations. GNS3 didn't save my configuration. So let me try that one more time. Show IP route connected. So really, come on. Let me see what's going on here. Loop back. Oh, Yeah, that kind of makes sense. It's been a long day. How about show IPv6 route connected? This would be a IPv6 configuration, so we're not doing IPv4. Probably what I ended up messing up the last time. Anyway, so I can see that I have several different connected networks. I've got Ethernet 1/3, which is the 2001 DB8 A01-1400 network. I've got a couple of loopbacks here, and I've got an Ethernet connection, which is Ethernet 1.0. If I go to my GNS3 topology, that's this connection that goes over to the internet device, and that simulates that internet device. So I got these two loopbacks here, and I've got this link A01-1400 that goes between the two routers. So if I take a look at, say, for example, show run interface Ethernet 1/3, show run interface Ethernet 1/3, you can see that I've got a global unicast address assigned to the interface, and I've simply enabled RIP on the interface by typing the command IPv6 RIP CCNP_RIP enable. Now, if I was to do that without enabling the RIP process globally first, then the router would automatically create the routing process globally, and it would enable the process on the router. If I do a show interface Ethernet 1/3, you can actually see, show IPv6 interface Ethernet 1/3, you can actually see that this interface is participating in several different networks. It's got a link local address, which was derived from its MAC address using the EUI64 process. It's got a global unicast address assigned to it, and then it's also joined all these different multicast groups. All hosts, all routers, RIP, multicast group, and then we have these duplicate address detection groups that are used for discovering whether or not somebody's using the address that I'm using, and so on. So we can see that RIP is running on this router. I can do a show IPv6 protocols, and I can see that the routing protocol CCNP RIP is running, connected routing is running, neighbor discovery is running, and these are the interfaces that the protocol is running on. All right, so that's our foundation. Now let's make sure that we continue to go through the exercise here. This is the topology. Obviously the goal is to get these two loopback routes to show up in router 2. This is going to show up as a connected route in router 2. And then also to get this loopback over here on router 2 to show up in router 1. And then we also have a default route on router 1. Show IPv6 route static. We have this static default route that points out the Ethernet interface. And we want to be able to get this default route, which represented as a :/0, because this isn't a default route, quad 0/0. Well, :/ in this case simply means all zeros. You can represent any consecutive string of zeros as a :/. And that's what we're doing in this case. We're representing 128 zeros as a :/. But you can only use it one time. All right? And then the prefix linked is /0. This is the administrative distance, and this is the metric. Static routes don't have a metric. All right? All right. In your book, they've got a table that describes all the addresses. This is the part that you guys probably should pay attention to, because the diagram here doesn't match what we built in GNS3, but I did put the labels on the interfaces. So if you guys do decide to go through and play around with these labs later on, make sure you just pay attention to the interface numbers, and you might even want to write it up in your book and make a change in your book to be able to kind of map everything. All right. So what do we need to do to be able to configure RIP on our network? Well, number one, you have to enable IPv6 routing. Unlike IPv4 routing, IPv6 routing is not enabled by default. Number two, you need to enable the RIP next generation routing process, which has a locally significant name. Okay? Locally significant name. We probably will want to make it match on all the routers, but the name itself is not propagated in the routing updates. So even though it's called CCNP underscore RIP on one side, or whatever it's called, it doesn't necessarily have to be called that on the other side. And then we enable IPv6 on the interfaces by either assigning an IPv6 address to the router interface or by typing the command IPv6 enable. Now that won't give it a global unicast address, but it will cause the interface to generate its own link local address. And actually routing information is exchanged using link local. You can actually learn about routes through the link local process without actually having to use a global unicast address. And then the last step is enabling RIP on the specific interface. All right, so let's go through this process step by step. The first thing I'm going to do is I'm going to go into router number 2, and I'm going to enable, if I come in here and I type show IPv6 protocols, you can see that I'm not running RIP. It looks like I am running IPv6 routing. So I probably already have that command in here. Do show run pipe include IPv6. Yep, it looks like I already have some IPv6 on here. So the first step would have been to enable IPv6 globally using this command, IPv6 unicast routing. So I'll just do it anyway. IPv6 unicast routing. That turns on IPv6, the protocol stack on the router. All right. The next step is to enable the RIP routing process. We type IPv6 router, and you can see here we have several different options: EIGRP, OSPF, and RIP. So we use a similar process in configuring EIGRP and OSPF. In this case, we're going to enable RIP, and then we specify a name. I'm not sure how large that name is. I think it's a 32-bit field, but I could be mistaken. The name, the name itself can't contain special characters. It can't contain spaces. So we're just going to keep it simple, and we're going to type the same name that we had on the other router, which is CCNP underscore RIP. Again, the name does not have to match on all the routers. By the way, I think I did mention this, and I misspoke. If you try to enable IPv6, in fact, let me do that real quick, just to demonstrate the concept. So I'm going to go into my router, and I'm going to take out the routing process. Do show IPv6 route connected. So I'm going to go into interface loopback 0, and I'm going to say IPv6, and I'll just enable it, trying to enable it on the interface. IPv6 RIP, give it a name, CCNP underscore RIP, and then type enable. All right. So remember what I told you guys? I said if I try to type this on the interface, is it going to create the routing process globally for me? If I do a show IPv6 protocols, you can see that it actually did enable the routing process globally on my router, even though I hadn't actually technically entered that command. The point that I'm trying to make about this, and this is very important, is that if you mistype the name, it's just simply going to start another routing process. It's not going to give you an error and indicate that you mistyped something. The book actually is wrong. Page 55, it actually states that if you try to enable RIP on an interface, well, actually, that's not what they're saying here. They're saying if you try to enable RIP without enabling IPv6 unicast routing, that will give you an error. And absolutely, that's 100% true. I just misread what they were stating there. So that's absolutely true. If you don't enable IPv6, the IPv6 protocol stack, it's not going to allow you to enable or engage in configuring an IPv6 protocol. Okay? But I guess as a secondary side note, you can apply a RIP routing process to an interface that doesn't exist and it will create that process for you globally. All right. So if I do a quick show run, do show run pipe section RIP, you can see that the global process has been enabled, plus I have the single interface command. I can tell this is an interface command because it has this space, it's indented, as opposed to left justified. Left justified are my global commands, and then the ones that are indented are related to some sort of sub-interface command or sub-configuration command. All right? So let's go ahead and enable RIP on our interface. Actually, let's not do that just yet. I did it on the loopback, but let's not do that just yet. Let's do a quick show IPv6 interface brief. And by the way, that's another point I want to make with you guys here. All the commands and everything that we learn about in IPv4, because we're going to be doing a lot of IPv4 with OSPF and EIGRP, almost completely interchangeable with IPv6. Show IP OSPF neighbor, show IPv6 OSPF neighbor. Show IP OSPF database, show IPv6 OSPF database. Show IP route, show IPv6 route, and so on. So everything that we're learning in the IPv4 space is portable over to IPv6 by replacing typically the keyword IP with IPv6. So let's do a quick show IPv6 interface brief. And again, the one thing that I just want to point out here is the fact that we have not only our global unicast address, but we have our link local address. And these link local addresses won't match up with the book, obviously, but you can also statically configure these. Additionally, what's in the brackets here indicates the physical layer and the data link layer. The first up represents the physical layer. The second up represents the data link layer. So you can see administratively down, that means that the interface is shut down. If you just saw down, that means that there's some sort of physical layer problem. If you saw up, down, then you have to troubleshoot layer 2 and so on. All right. We already talked about what link local addresses are used for. Very, very important concept. Link local addresses play a significant role in IPv6, especially with routing protocols. Neighbor relationships are established with link local addresses. Next hops in the routing table are defined by the link local address. Neighbor discovery, which is IPv6 equivalent to ARP, is done with link local addresses, all kinds of things. Okay. However, link local addresses are not routable. All right. So let's go ahead and finish up our configuration. We need to go into interface. We already did our loopback interface, so we need to go into interface Ethernet 1.1 and set up our CCNP RIP on that. So interface Ethernet 1.1, and I should just be able to do my up arrow. There we go. All right, if I do a quick show IPv6 protocol, I can see now that CCNP RIP is running on both loopback 0 and Ethernet 1.1. Okay. So we did step number 1, enable IPv6 routing on the interface. We created a RIP next generation routing process. We already had addresses assigned to our interface, so we didn't have to do that part. And then finally, we enabled RIP on the interface itself. All right. Now let's see if we're getting our routes. If I go on to router number 2, I should be seeing those 2 loopback routes that we saw that exist on router 1. Show IPv6 route. Let's do RIP. All right. And sure enough, there's the 2 loopback routes. Notice the next hop. Well, let me break it down. R is the code. That's how we learn the route. The table's a little bit messed up on the formatting here, but connected, local, static, and R is somewhere in here. There it is, RIP. Okay. So we're seeing in this particular case a RIP route This is the destination prefix. Remember, an IPv6 address is 128 bits in length. Each one of these blocks represents 16 bits. So this is actually the network ID. This is actually the network ID. This is the 48-bit prefix for the entire enterprise. So this would be equivalent to what you might see in your own network, where you went to the ISP and you said, hey, we want to run IPv6, and they assigned you 2001 DB8 A01 /48. And that became your prefix for the entire enterprise. And then on top of that, you decided to subnet. The first subnet was subnet 100. The second subnet was subnet A00. The third subnet, whatever it might be. So this represents 64 bits of ones and zeros, which represents the network ID, which is what routing tables show us, right? The routing tables show us the network ID. 120 is the administrative distance. Hop count 2. Now that's interesting because this is different than it is in IPv4. Remember, we're talking about router 2 over here reaching these loopback networks over here. You're like, well, wait a minute, why is that 2 hops? Because I go out of this interface, I go through this router to the loopback, that's only 1 hop. In IPv4, that would be the case. But in IPv6, router 2 adds itself as a hop to those routes. So that's why we're seeing a hop count of 2 in this particular case. All right. All right. Now the next step, which is the last step, I know we're a little bit past our time today, but I wanted to finish up this module today for sure, is what do I do about the default route? Now certainly in this topology, I could just go ahead and put in a static default route that points to router 1, and we'd be good to go. All right. But think about this from the perspective of maybe there's more than one path to router 1. Maybe there's multiple paths, and I want to make sure I'm choosing the best path. So my best option would be to somehow inject the default route into the routing domain through the RIP routing process, so that if one path fails, then another path comes up or whatever. I'm going to go ahead and still be able to route to the internet based on that decision. All right, so in the case of R1, oh, by the way, I'm sorry, I should have mentioned this. These are all the configurations that we applied, IPv6 unicast routing and so on, and the show IPv6 interface brief up, we looked at that. And then this was the configuration commands. These were the configuration commands that I applied to the individual interfaces. The show IPv6 protocols, I don't know why I was not switching through these slides. I guess I was just showing you in the command line. Shows me that CCNP_RIP is running on these interfaces. And that's very important. That's a very important distinction, by the way, guys. OSPF, EIGRP, RIP, they all work the same way in IPv6 in respect to we enable the protocols on the interface. There are no network statements, no wildcard bits, no area commands, although, well, in OSPF we still have the area command, it's just done on the interface. So rather than creating network statements to include interfaces to run the protocol, we simply enable the protocol directly on the interface itself. All right. Here's our routing table that we looked at. Show IPv6 route. We can see the 2 RIP routes, 120 with a hop count of 2, and the link local address as the next hop. That's, by the way, that's the reason why I like to kind of change those link local addresses, because I don't want to look at those big, long, confusing link local addresses. I'd rather come into, say, router 1 as an example and do show IPv6 route connected. I can never remember which interfaces I'm using. No do. So config T interface loopback 0 IPv6 address FE80:1 link local, and let's do loopback 1 as well, and let's do Ethernet 1.3. And Now let's see what that looks like from router 2's perspective. All right. Now this is an interesting concept. Again, something that RIP is flawed with. It says, oh, I can get to that network now through two different addresses. I can get to it through FE80:1, and I can get to it through this address. Show IPv6 protocols. Let me see if a summary will show it. Show IPv6 RIP. There we go. That's what I wanted to show you. So this is the problem with RIP. This is the process that I'm running. I use the command show IPv6 RIP. This is the port that it runs over. This is the multicast group. This is the process ID if you want to monitor memory utilization and so on. Administrative distance and so on. Sending out updates after 30 seconds. A route expires after 180 seconds. And then we don't see the flush timer here, the hold timer. But essentially that route is going to stay in the routing table for 180 seconds. And then after 120 seconds after that, it's going to get flushed out. So as I'm going through and I'm looking at the routing table, eventually what will happen is it will say this route is possibly down. You'll see a possibly down next to it, and then eventually it'll flush it out. That's part of the slow convergence process of RIP. RIP is just really slow. It's as a traditional distance vector routing protocol, it doesn't always trust the information that it's learning, and it doesn't know how to make a decision on what to do when something changes in the network. Okay, so I prefer this. I mean, I wouldn't probably use something this simple because I may want to use something that's more indicative of what the position of that router is, or what, maybe I can use a building number, or I don't know. I mean, you can get creative, but the link local address can be the same on every single interface because it's a non-routable address. All right, it's a non-routable address. So eventually these guys will go away because this one will continue to show up in the updates. All right. All right. Wow. I just got a mess. So these are the kinds of things that I'm going to be showing you guys throughout the class. I mean, I know RIP isn't all that important, but this is more related to IPv6 than anything. The main thing is I don't just want to do what's in the book. I want to show you things that I would consider as important things to consider when you're in a production environment. And of course, it'll be more important when we get into the protocols that actually mean something to you guys, like OSPF and EIGRP. So there we go. The route finally disappeared after the 3 or 4 minutes that it took for RIP to kind of figure it out. So I've got this default route. If I do a show IPv6 route on my guy here, you can see that show IPv6 route. You can see that I don't have a gateway of last resort. I've got a null zero route for my multicast, which is essentially a summary null zero route, but I don't see any default route. I don't see a :/0 route. So there's a couple ways that we can inject that route. I can go into router 1 and I can say default information originate, much like we see with OSPF in IPv4, the default information originate option. But I have two choices. I can do originate or I can do only, default information only. And what that does is that basically suppresses all other RIP routes. And router 1 will only send a default route into the RIP domain, into router number 2. All right. This is done on a per interface basis. Unlike OSPF, where you do it under the routing process, we go to the interface where we want to originate the default route, and we specify that on the interface itself. All right. So in this case, we're going to put this on Ethernet, in our topology, Ethernet 1.3, and we're going to go ahead and start by putting in just the standard originate command and not the only command. All right. So let me go ahead and go into router number 1. Config T, config T, interface Ethernet 1.3. Wow. And let me paste in, or put in that config. IPv6 RIP, CCNP underscore RIP, default information, originate. Okay. That's going to force a triggered update. And as soon as that should, well, it didn't force a triggered update. Let me see. Probably have to wait until, make sure I did the right interface. Gosh, dang it. Show, let's see, 1.3. Yeah, I did the right interface. So eventually that default route should show up, and sure enough, there it is. Notice the next hop is link local. A lot cleaner when you have that nice clean link local address there. And this is the default route. Same metric, 2 hops. Learn through the RIP process, same administrative distance. Okay, but we still see also the other RIP routes in the database as well. All right. All right. Obviously, you know what's going to happen if I do the only command, then those other 2 routes will disappear. All right, so the last thing we're going to do for today, and I promise we're almost done here, is to go ahead and take a look at the database, because that's an important part of analyzing any protocol, is to look at the database. Here's an example where I see the default route on router 2 after I did the originate, and here's an example of what it would look like if I changed it to only, and then I lose the 2 loopback RIP routes. Eventually, it would take a couple of minutes for them to disappear, and then all I would see is the default route. All right, so the last part of this exercise is taking a look at the RIP database. I already showed you this command, show IPv6 RIP, shows us the RIP routing process, the fact that it's running in over UDP port 521 in this case. Maximum paths is 16. Any idea what maximum paths represents? Any thoughts?
Hops, right?
No, actually in this case it does not represent hops. It represents the maximum number of equal cost paths that I will load balance over by default. In IPv4 it's 4, in IPv6 it's 16, in IPv4 it can go up to 16, in IPv6 it can go up to 64. So it's actually, I understand why you said hops, because maximum of 16 is the maximum hop limit, but in this particular case it's actually referencing the maximum number of equal cost paths that I'll put into the routing database if I have that many paths.
I'm trying to imagine a scenario that
It would never exist. Yeah, it would.
All right. Okay.
I mean, if you got 16 equal cost paths to a destination, and you're using RIP, there's something seriously wrong. But in any case, I mean, why would you ever have 16 equal cost paths? But all right. The rest of it makes sense. Updates every 30 seconds, typical for a distance vector protocol, traditional distance vector protocol. Expires after 180 seconds. That's why we saw those routes stay in the routing table, even though we vacated those routes from the routing table. And then the last thing we'll look at, which is the last slide of today, is the RIP database itself. Now in EIGRP, we're going to call this a topology table. In OSPF, we call it a link state database. In RIP, it's just simply called the database. So let's go into router 2 and do a show IPv6 RIP database. Now the reason why this is, just cannot type today. The reason why this is a particularly important thing to understand is because you not only want to see the routes that you're potentially learning from other routers, all right, like the first 3 in the list. You also want to see maybe a default route, but it tells us When does that route expire? Okay. Now that number really should not go below 150, right? Because we should be getting updates every 30 seconds, and the expiration timer is 180 seconds. So as I move down to 150, sure enough, I get another update, and that resets that trigger. So if you're trying to troubleshoot whether or not a route is valid or a route's being updated, you can do it this way. You can take a look. And there's not much else to this output here other than that. You see the next hop. You see the exit interface. It's written in kind of a weird format, but this is the exit interface, and then this is the next hop. This is the prefix, and then this is the metric. And whether it's installed in the routing table, that's an interesting concept as well. What would cause a route to not be installed in the routing table? What if?
No route.
Um,
Well, that's opposite. No route, you put in no route to be installed.
Correct. So what would cause a route to not be installed would be if you're learning about the same prefix from another source that has a lower administrative distance. Say I learned about this prefix through OSPF. This route would not be installed in the routing table. It would be in the database, but it wouldn't be in the routing table.
But not the routing table. Okay.
Exactly. So the database doesn't necessarily reflect your routing table. It just simply reflects everything you're learning through the RIP process. All right. All right. Yeah, I guess that's about it. I mean, that was a very basic discovery, but I think there's some good stuff to take away from that. Yeah, and that basically concludes module number 1. All right. And so what we're going to do in module number 2 is focus on EIGRP. There are actually 5 different lessons in module number 2. And we're going to learn all kinds of wonderful things about EIGRP. All right, so that ends day number 1. Let me stop these recordings.